Today, I will be presenting a topic like my hobby. Audio fingerprinting is one of them. How Shazam identifies song in 5 seconds. We will see that tomorrow together, and we will build a mini Shazam with Python together, and we will try it. First of all, thanks for presenting, by the way. I'm working as an AI engineer at ING, and audio fingerprinting is not one of my job studies, but I like this type of topics. So here's our plan today. We'll start with the big picture of how Shazam works. Then we'll go step by step from sound waves to spectrograms, finding the unique parts of the song, building fingerprintings, and matching them in database. After that, we will build a small version together in Python. And we will talk a little bit about the real world problems and finish the other uses. So, what is Shazam? Simply put, it's an app that listens for a few seconds and recognizes the song. It has come a long way. Back in 2002, you actually called a phone number at that time and held your phone to the music. I was at like 3 years old at that time. In 2008, it became an application. By 2012, it moved beyond just music. Today, it's like the part of the Apple. It feels like magic. Do you all also think like me? But I don't know. It's like really clever engineering. There are 3 main steps. First is capture and simplify the audio. Then we turn it to the spectrogram and find its fingerprints. And finally, we do a very fast search. We will look at each of these. Everything starts with the sound of itself. When we record an audio, the computer stores it as many small samples. On this chart, you can see the X is the time, so when the sound happens, and Y is the amplitude, how loud it is. This is just my voice saying hello world. I captured it. Before we record, we set 3 things. The sampling rate, bit depth, and channel. The sampling rate is how many times per second we measure the wave. Bit depth is how detailed each measurement is, and channel is how many audio tracks we record. In here, we use mono channel, which means we record a single track. These are standard CD quality settings I put at there, like the sampling rate is here, bit depth and mono. Here's how to do with it Python. We use the sound device library to record. We tell it the sampling rate, the duration, and that we want 16-bit mono audio. After recording, we take the first 1,000 samples and plot them, which gives us the wave you see earlier. Why sound device? It's simple. Once install command and you can record a play audio directly with Python. It does a hard work talking to your microphone for us. So, there's a problem. How to understand sound waves? A raw sound wave mixes everything together, the voice, the drums, the guitar, all in the way. And it's too messy to identify a song from this. What we really want to see is to see frequencies hidden inside the sound. To do that, we create a spectrogram. This is what a spectrogram looks like. I recorded about 10 seconds of the song Şımarık by Tarkan. It's a famous song in Turkey. And this is the result. Instead of one line, now we can see how the sound is spread across different frequencies over time. You can see on the colors in the chart. Let me explain how to read a spectrogram. Time goes along the x-axis and frequency in hertz goes up in the y-axis. The color shows the power or loudness. Brighter means louder in here. So each vertical slice tells you which frequencies are present at that exact moment. How do we build one? We use something called short time Fourier transform. The idea is simple. We cut the sound into small overlapping windows, and we apply a Fourier transform each one. This lets us to see how the frequencies change over time instead of looking at the whole song at once. In Python, the LibRouser library does this for us. We compute short-time Fourier transform, then convert the results to decibels so it's easier to read. The last few lines in the cloud, just plot it with nice colors. That's all it takes. I will also share the codes in the repository. So, why LibRouser? It is the go-to library for audio analysis. In Python, it handles spectrograms, frequencies, and many other audio tasks. So we don't have to write it mathematically ourselves. Now, we don't actually need every single point of spectrogram. Instead, we look for the strongest points, the loudest moments each frequency. Each strong point is like a star in the night sky. Together, these stars form what we call a constellation map, and this is the real fingerprint of the sound. Let me show you. Every song has its own pattern of peaks. On the left is the full spectrogram you can see in the slide, and on the right are just peaks I detected from the same Tarkan song. Notice how much simpler the right side is. We've thrown away the noise and kept only what matters in here. How do we find these stars? We look for local maxima, points that are louder than all their neighbors. The process has 3 steps. We slide a window across the spectrogram. We keep points that are stronger than their surrounding area. And finally, we keep only the top 10% strongest ones. The result is cleaned constellation of the song's brightest moments. And here is the final constellation on its own. This is now simple set of points, much easier to work with than a full spectrogram. This is what we'll use to identify a song. In Python, we use a maximum filter from SciPy to find the local maxima. We also set a loudness threshold using a percentile, so we keep only the strongest peaks. Then we just plot them on top of the spectrogram. Now, we have our stars, but single points aren't enough to search for. A single peak isn't unique. Many songs have a peak at the same frequency. So the next step is connect the stars into patterns. Just like how we connect stars, a form of constellation we can recognize. Here's the key idea. We take each peak and connect it to few nearby peaks that come little later in time. Each pair gives us 2 frequencies and time gap between them. This combination is much more unique than a single point. Then we turn each pair into a short hash, a kind of a compact code. That hash is our fingerprint of the song. This picture shows those connections. The blue lines link one peak to another ahead in time. Each line becomes one fingerprint. A full song produces thousands of these. In code, we loop through the peaks and connect each one its next few neighbors, the fan value, as you can see in the code. For each pair, we calculate the time difference and create hash in the hash library. At the end, we have a list of hashes that represent the whole song. Now, we need to store all of this. We use two tables. The song table holds the title, artist, one row per song. The fingerprints table holds each hash, the song it belongs to, and time offset, meaning where in the track that fingerprint appears. Setting it up is easy with SQLite. We create the two tables and insert each fingerprint with its hash, song ID, and offset. Later, when someone records a clip, we search this table for matching hashes. Why SQLite? It's lightweight, no server, needs no server, which is perfect for demo. I will show you. And it's also fast, so it's easy to move around. This is one of the clever parts of the talk. First, we take the fingerprints from the short clip and search for matching hashes. For every match, we calculate the time difference between the clip and the original song. Then, exact match votes for a specific song and time alignment. The correct song is the one with the most votes with the same time difference. This is why noise doesn't fool it, random matches don't line up, but the real song does. Here's the matching code in Python. For each fingerprinting in the clip, we look if it's hash in the database. For every result, we calculate the time difference and add a vote that song and that delta. We just count the votes in a dictionary. Sorry. Finally, we find our winner. We simply pick a song and time difference with the most votes using max. The highest score means the strongest time alignment, and that's our answer. The song is identified. So let's build a mini Shazam together. Our mini Shazam will record a short clip, extract its fingerprints, compare them to the database, and return the song with its best time aligned matches. Let me show you. By the way, I also shared the QR codes of the demo. We can do demo right now. Okay. Now it's our simple mini Shazam. I put like 5 songs into database, not too much, and I just pick my favorite ones. So I will try the songs, and I will also take some suggestion from you. Obviously, I wasn't edited it into the database, and we will see if it works or not together. So when I put into the listen, one of the songs that I added, let me open. Sorry for the delay. Okay. It's too loud. I was just saying, sometimes demo can't work. And I will also open another song. Then I will take a suggestion from you. If you like to do that, give me a suggestion for now. You can suggest me a song. Any of you? Michael Jackson. Oh, sorry, my internet connection. Thriller. It's not in the database. I will. Yes, it's not in the database. I didn't edit it. And we can also try another if it works or not. It's also a Turkish song. And I also edit Bella Ciao. Yes. Like in here. I hope I edit. Thanks. Thankfully. And that's how we built Mini Shazam. I will also share the repository. Let me open the slide. So, this is also one of the screenshots of the app, and it was an example in the slide too. I built the interface with Streamlit. Why Streamlit? It lets you to build interactive applications just in minutes. It's great for data and machine learning demos also, and perfect for a project like this. Of course, the world is harder than the lab. There is background noise, distortion from the speakers and microphones, time offsets because the clip can't start anywhere in the song, and the huge challenge of scale. Thankfully, we didn't leave one of them, but if we don't open the voice of the song, because it's too simple application I put at there, it may be not detect even if it's on the database. Because yes, it just connects the peaks, but I just built in the original song. So it may be effects of that. And also fingerprinting isn't just for music. The same fingerprinting idea is used for speaker identification, detecting environment sounds, tracking TV ads, monitoring industrial machine for faults, even some medical applications. It's surprisingly flexible tool. So I actually finished my earlier I expected. I can answer any questions. So I'll be.
So thank you. Thank you, Özge. I love this tool. I have to be honest. And as a teacher, I think that I could show my students how to build a mini Shazam. So thank you.
Thank you.
We have a couple of questions from Slido. Pietro asks, in constellation plot, there was an initial part close to t equals 0 for all frequencies, while the rest only shows local maxima.
Yes.
Why?
To get only for the peaks, to get the song's fingerprinting, we don't need all of the points of the song. We just need for the important, the louder points, and the local maxima shows us that. Okay.
Okay, Pietro.
Maybe.
Wait for the microphone. They will fire me.
Sure. Thanks.
Let me check.
If you go to the second plot, the one you found maxima for.
Local maxima.
Yes.
I'm checking right now. Sorry.
No problem. Yeah, I think it's
yes.
next slide. Yeah. So
This
what I
one.
was saying, in the second spectrogram,
Yes.
there is a part of the plot close to T0 where you still keep the whole, it seems at least from the plot that you still keep data for the whole frequency range.
Yes.
But
it's a frequency range.
Okay.
Yes. And we are only getting the local maxima. This frequency range is the local maxima of the left in the spectrogram.
Mm-hmm. Okay.
And why is that?
To detect
what is the reason behind just the
so like
tiny line?
The
yes,
tiny little
yes.
bar, yeah.
The reason the left one, using only the spectrogram is too confusing to understand because there are too many songs and there's too many kind of spectrograms looks like each other. Maybe we can't detect that. To detect the point, they needed to understand what is the specific thing, what is like the peak, what is the unique. And they just choose that, and also they applied on the short time Fourier transfer, and I think it's clever engineering because it was like 2000. You know, it's been years, and
yeah, good. Thanks.
Thank you.
Okay, and the next questions, always from Pietro, was can you play a few seconds of the song you used for the analysis while showing the plot?
Which one? This.
This song.
Şımarık? So I need to check the whole code because it's all on the repository, but not like I didn't prepare for demo. We can see you together later.
Okay, so next question from Michele. How does recording noise interact with the hashing step? Since hash functions are highly sensitive by design, is the building of the constellation map supposed to remove noise?
To remove noise, yes.
Okay.
It's a different kind of problem. Actually, if they are detecting the peaks to remove the other things, one of them is noise, but it's too simple idea of it. It doesn't employ any noise in the code, so I can't do that. But doing the short-term Fourier transform, like repeated times, is also helps to detect the noise of the sound.
Okay, and then another question. How many point couples we need to store for each song in order to get a precise recognition?
Actually, I can tell you because it was writing at there. Let me check if I didn't. Maybe I can just work this and I will check right now. It's not seems to you, but for example, I also added a song like, do you know Woodkid Run by Run song? It has at least 20,000 fingerprints it has on. Each song in the database, it just, I wrote the fingerprints, like We Are the People of the Empire of the Sun has at least 50,000 fingerprints.
We are not watching your screen, by the way.
Yes, I know, but
okay.
maybe, oops. Where is it? Sorry. I can't see my...
Okay.
Can you see now?
Yes, thank you.
For example. I can't see clear, but as you can see, We Are the People in the last one has at least 50,000 fingerprints. And I also shared the whole codes in the GitHub. It's been staying at there like a year. You can contribute if you want.
Okay. Okay, so next question. How efficient is this approach for different versions of the same song? For example, live versus studio recordings.
Yes, yes. Also, it can. You need to do the record like live and the original version, both of them into the database, because this is too much simpler version. As I searched about the latest work on Shazam, they changed their kind of style. This is their first building the magic like that. They put some AI into it, as you can guess. So this version, you need to add two type of into the database. Okay. Yeah.
And then last question from Slido. If you want to make a question here, feel free to do it. Any idea how Shazam handles scale of their queries?
Actually, I have no idea for now. I need to check.
Okay. So no, we have no idea.
Yes.
Any other questions from the room? Yeah.
Hi, thank you for the presentation.
Thanks.
I would like to ask you if the local maxima technique is the golden standard for...
Yes, yeah, I mean, I was just switching to my language. I mean, it was gold standard for this fingerprinting type of, but not golden standard for now.
Okay.
Yes, because the techniques are changed. Machine learning comes in. There are another techniques to do that. So, but at that time, this was the golden standard.
Okay, and have you tried with something else, like
No,
the mean?
in practice, I didn't try anything than that.
Okay, thank you.
Thank you.
Any other questions?
Hi, thanks very much for the talk.
Thank you.
Are there any like inherent differences between like different musical styles or anything that would make it more complicated than a different song? Like, I guess
Yes.
the question is, if you wanted to reverse engineer the most unshazamable song, what would you have to do?
It's a good question. Actually, as I understand correctly, you asked me adding too many songs in this database, right?
No, I mean like, is there like, for example, like a rap song that samples another song? Is that more inherently complicated for the algorithm to understand, or?
I don't think it's just about the genre. It's also about the detecting the peaks, I guess. If we are looking it in technically, but I have no idea.
Thanks very much.
Thank you.
Okay, any other questions from the audience? Okay, perfect. So let's thank together with an applause Özge.
Thank you.
Very interesting talk. Congratulations. I have to remind you that today is Pi Dinner Day. We still have some tickets available. If you want to join us tonight, you can go to the registration desk. Thank you for being here.
Thank you.